In this video, we'll explain photoelectric effect that will prove the corpuscular aspect of light, which is chapter 16 for LS and GS. But before starting our chapter, let us make a brief introduction about what is light. In 1637, a French scientist, René Descartes, introduced the corpuscular theory of light, which states that light is made of a small discrete particles called corpuscles, which travel in a straight line with a finite velocity. In 1678, a Dutch physicist, Christian Huygens, utilized the theory of light as a wave to explain the light reflection and refraction phenomenon. He proposed that every point to which a luminous disturbance reaches becomes a source of spherical wave. Here, a plane wave, and the red dots are secondary circular waves. The yellow dots are secondary circular waves that produces forward spherical waves. At the same period, there was an English physicist, Isaac Newton. In 1672, he was a pioneer of the corpuscular aspect of light. And Huygens made stormy debates opposing Newton's light particle theory. In Newton's corpuscular theory, he proposed that light consists of different sizes of particles. And because of the different sizes of this particle, we can see different colors. These are the corpuscles, small particles that gives us different colors depending on their sizes. And he explained the reflection as particle and refraction of light, same as a ball reflect on the ground. But he couldn't explain diffraction and the interference of light. Newton's theory was predominant for more than 100 years and took precedence over Huygens' wave theory of light. In 1807, English physicist Thomas Young showed that when light coming from a point light source is shined on two pinholes, they will interfere with each other, and interference fringes can be observed on the screen. Young's experiment advocated the theory that light behaves like a wave. And by Young's double-slit experiment, Huygens' wave aspect of light was proved. In 1862, a Scottish scientist, James Clerk Maxwell, theoretically predicted the existence of electromagnetic waves. The fact that electromagnetic waves propagate at the same speed as light. And this is the electromagnetic wave. The blue one is the magnetic field, while the red is the electric field. We can see it from this position. Here's the propagation to the right now. Maxwell published a set of equations, proved that light, electricity, and magnetism all came from the same force, electromagnetic force. Maxwell's equations for electromagnetism have been called the second great unification in physics, of course after Newton's. In 1887, a German physicist, Heinrich Rutherford, built a spark generator, and he put far from it a receiver antenna, and he got a spark at the gap of the antenna. We can see this experiment. This is the spark generator, and here the receiving antenna. We are getting the bulb lighting. The bulb is lightening. Even if we take the receiver far from the generator, we're still getting the spark. But Hertz couldn't explain what's going on. In 1900, another German physicist, Max Planck, proposed that energy is not continuous, but rather is quantized. That is, all energies are multiples of a smaller fundamental unit of energy, which is Planck's energy. And his postulate state, electromagnetic energy could be emitted only in quantized form. In other words, the energy could only be a multiple of an elementary unit, which he called Planck's energy. So the energy equal to h times nu, where h is Planck's constant, 6.626 times 10 to the power minus 34 joules second. And nu is the frequency of the radiation. This is a new symbol. We will use it instead of F for the frequency of the radiation. In 1888, also another German physicist, Wilhelm Hallux, who was the assistant of Hertz. In 1887, they carried the investigation of electromagnetic waves. We all know the electromagnetic waves starting from the radio till the gamma ray, and they focused on the ultraviolet radiation, which has a high frequency and short wavelength. Its frequency higher than the visible light. And in 1888, Hallux formulated the hypothesis that a conductive plate on which to focus ultraviolet carries a positive charge because the electrons are emitted. The phenomenon was called Hallux effect. Now we call it the photoelectric effect. But Hallux couldn't explain what's going on. After that, a Hungarian physicist, Philip Leonard, his experiment in photoelectric effect inspired Einstein. He said the maximum kinetic energy of the electron emitted does not depend on the intensity of the light, while it depends on the frequency. In 1905, Albert Einstein solved the problem, a German physicist. Einstein extended what Planck said and predicted that also light must be made of quanta, and he called them photons. Einstein proves again the corpuscular aspect of light and named these corpuscles photons. In 1924, a French physicist, Louis Victor de Broglie, he postulated that wave nature of electron and suggested that all matter has wave properties. This concept is known as de Broglie hypothesis, an example of wave-particle duality.